During the last couple of weeks, we've been talking a fair amount about Taylor polynomials and then infinite series of real numbers. The goal is to eventually put these two ideas together to take a closer look at what are called Taylor series. And as a first step towards that, we're going to begin to discuss today what are known as power series and the interval of convergence. A power series is an infinite series of the form, the sum from k equals 0 to infinity, of c sub k x minus a to the k power. A is some fixed quantity here, and x is considered a variable. Now this is sort of reminiscent of the Taylor polynomial. We have an a here, but instead of various derivatives of f, we have just coefficients c sub k, and then instead of stopping at, let's say, the third or fourth or fifth term, the thing goes on forever. It's like a polynomial of infinite degree. During the next few minutes, we're going to be taking a look at the following example, the sum from k equals 0 to infinity, k over 2 to the k times x minus 3 to the k power. If k is 0, of course, we get 0. If k is 1, we get 1/2 x minus 3 to the first. If k is 2, we get 2/4 x minus 3 squared, and so on and so forth. The goal is to determine, really, what values of x can I plug in here so that the series converges. Let's experiment a little bit. Let's suppose that x is 4. If x is 4, and if I plug that in here, I get 4 minus 3, or 1 to the kth power, which is just 1. So I'm looking at k over 2 to the k, summed from k equals 0 to infinity. This is a good situation to use the ratio test to ascertain whether the series converges. So when I use the ratio test, my c sub k is k over 2 to the k. c sub k plus 1 is k plus 1 over 2 to the k plus 1. Now, to divide these fractions, we invert and multiply. And just like there usually is, we see a fair amount of cancellation. The 2 to the k here is going to cancel with all of this except 1 power of 2. So we'll have k plus 1 over 2 times k. As k gets really, really large, the 1 becomes relatively insignificant. So we have k over 2k, which yields a limit of 1/2. This is our L value, which is certainly less than 1, so that we know that the series converges by the ratio test. The ratio test by itself does not tell me what the series converges to, but I can approximate the sum of the series in this case by using, let's say, the first 50 or 100 terms, and I get about 2. And the way I did this is I used the GeoGebra applet that we've been using in the lab recently. Now we can experiment further with other values of x and determine whether the series converges. If x is 1 and we plug 1 in here, apply the ratio test, we'll get an L value greater than 1, so the series diverges. If x is 1.5, plug 1.5 in, I get a series that converges by the ratio test again. And if I use the GeoGebra applet, I can approximate the value to be minus 0.25. And you can see what's happening to the other values. When x is 2, we get a series that converges to about this. When x is 3, we get a series that converges to 0, because if we plug 3 in here, we actually would get 0. If x is 3.5, we'll get a series that converges to about 0.444, and so on for 4.5. However, when we hit 5, we apply the ratio test, the series diverges. Similarly, when x is 5.5, the series diverges. And again, all of these calculations were done using the ratio test. The interval of convergence of a power series is defined as the values of x for which the power series converges. So, in terms of this example, 1.5, 2, 3, 3.5, 4.5, they all belong to the interval of convergence because when x is equal to any of those numbers, the resulting series, when plugged in here, will converge. Whereas if we plug in 1 for x, or 5 or 5.5, the resulting series do not converge, and so those values do not belong to the interval of convergence. It ends up that the interval of convergence is always going to be symmetric about a. In other words, the interval of convergence is going to be the midpoint of the interval. Now, instead of using the ratio test for different values of x, we're just going to use the ratio test to nail the problem, so to speak, or to figure out the interval of convergence all at once. In other words, we're going to use the ratio test, but there will be the presence of an x term. So here's our power series. My c sub k is going to be this entire quantity with absolute values around it. Now, normally we haven't worried too much about the absolute values because our series have contained entirely positive terms. But now we have to recognize that x minus 3 could be negative. So I put absolute values around this. The k over 2 to the k is positive, so I can factor that out, and I'm left with the absolute value of x minus 3 to the kth power. If I look at the k plus first term, perform the same process, I get k plus 1 over 2 to the k plus 1, x minus 3 absolute value to the k plus 1 power. The ratio test says that we look at the ratio c sub k plus 1 over c sub k, which I've done, and again I inverted and multiplied, which is where the 2 to the k over k times absolute x minus 3 to the k power came from. Cancellation. 2 to the k cancels with all of this except 1 power of 2. X minus 3, absolute value to the k, is going to cancel with all of this except 1 of absolute x minus 3 to the first power. So I'm left with k plus 1 over 2, absolute value of x minus 3 over k. Now, as k gets larger and larger, k, not x, but k, this 1 becomes relatively insignificant. So basically, we're left with 1 times the absolute value of x minus 3 over 2. So the absolute value of x minus 3 over 2, that's our L value. And in order for the series to converge, we want L to be less than 1. Now, the way we can make that happen is cross-multiplying the absolute value of x minus 3 is less than 2, or using properties of absolute values, x minus 3 is less than 2 and greater than negative 2. If we add 3 to each side of the inequality, we get 1 is less than x is less than 5. On the other hand, if x minus 3 had been over 2 had been greater than 1, then we would get an L value of greater than 1, so the series would diverge. That's going to happen when x is strictly greater than 5, or if x is strictly less than 1. So our interval of convergence will include everything between 1 and 5, not including 1, not including 5, for right now. Notice how 3 is the midpoint. We know that everything to the left of 1 and everything to the right of 5 is not included. But we do need to take a closer look at the endpoints 1 and 5 themselves. We need to check them each separately. If x is 1, and if I plug that into the series, I get the sum from k equals 0 to infinity, k minus 2 to the k power over 2 to the k, and that actually simplifies to be just the sum from 0 to infinity of k minus 1 to the kth power. Now, if I write down the first few terms, I get 0, minus 1, plus 2, minus 3, plus 4, minus 5, and so on. Notice how the minus 1 to the k makes the series alternate. If we group together the terms, notice how the sum of these is negative 1, the sum of these is negative 1, and so on and so forth. So in essence, what we're doing is we're adding together infinitely many negative 1s, so the series will diverge. Similarly, the other endpoint, if x is 5, if we plug that into our original power series, we get the sum from k equals 0 to infinity, k over 2 to the k, which ends up being 0, plus 1, plus 2, plus 3. The numbers keep growing and growing that we're adding together, so that series diverges. So the conclusion is that the interval of convergence for the original power series is x less than 5 greater than 1. So it would look like this on the number line. Notice how 3 is at the midpoint. If x is chosen outside this open interval, in other words, if x is chosen to be 5 or greater, or if x is chosen to be 1 or smaller, the series diverges. So, to find the interval of convergence of a power series, First, apply the ratio test to find an open interval whose midpoint is A. Then, check to see whether each endpoint is part of the interval of convergence as well. And you need to do that separately, once for each endpoint. In this case, the endpoint of 1 and the endpoint of 5 were not included in the interval of convergence. It could be in other examples that both are included, or perhaps that one is included and one is not. For class, what I would like for you to do is work on the following 3 examples: the sum from k equals 1 to infinity, x minus 2 to the k over k squared, the sum from k equals 1 to infinity, x plus 3 to the k power over k, the sum from k equals 0 to infinity, x to the k over 2k quantity factorial. I want you to find the interval of convergence, and I want you to use good limit notation. See you then.